sort of like, it's used everywhere. Like apparently React uses this concept. It's used a lot in robotics. So maybe like at the end of the talk, Gokul can probably like give some insights if you know something about it. And yeah, it's pretty cool. So yeah, so I'm Madhav on Slack. That's
Okay,
my
I look like
handle.
I don't have.
And
If
there
it's
is
okay
another
with you, you
friend
can start
who will
actually
sort of be
speaking.
helping me out
And
with this
at the
talk
end of the
today,
talk, this is
and
going to
that
be
is
on
Kubi.
Kubernetes does stuff.
So you need to
And
know three things about
this,
Kubi.
when I read it,
One
it
is
was in
that
terms of
he loves walks and treats. He hates baths, and he's unaware of his heart melting potential. So, and there's a point to all this. It's not just random. I mean, obviously, one valid point is that dogs are extremely cute and they should be there everywhere. But there is a point to this. So, yeah, that's Kubi. And this is the basic outline for today. So we'll be talking about something called what is an automata. That's we'll go over what that fancy term means. It's not all that complicated as it sounds. Then we'll be talking about what is a model, what is computation, and then like combining those terms and what is a model of computation for what we're talking about today. And then the actual topics, which is imperative, something called as imperative systems, something called as declarative systems, and then a demo, like based on the time, I'll either try to live code it, but if we don't have that much time, I'll try and I'll probably just run it for you, and all of the code is there on GitHub, so you guys can play around with it and ask questions on Slack or anything of that form is fine. And then after the demo, we'll sort of take a step back and we'll see how whatever we learned today relates to this thing called Kubernetes that I was talking about. So first things first, I saw that there were quite a few first years. So like, I'm not going to like assume that some terms are known. So first term is that what is an automata first of all? So an automata is basically a, a tool that you would use to model a process. And when I say a process, it's just a fancy way of saying that a sequence of getting things done. So suppose you are at one place, let's say you are at place A, but you need to get to place B. And to get to place B, you need to walk 500 meters. Or if you are at place and you need to get to place B, and to get to place B, you need a signal from someone who is at place B that, okay, can you please come here or something like that. So when you are at place A, that is called a state. When you are at place B, that is also called a state. And that process and that action of you walking from state A to state B is called a transition from one state to another state. So that whole thing, that is state A, state B, transition, that whole thing together is something known as a finite automata. Finite because you have a finite number of states in your system. So you have a state A and you have a state B. You can't have an infinite number of states, and you can't have an infinite number of transitions in a finite automata because it's called finite. And then you have something called a start state, which is where you start off from. So in the example that I just said, that would be state A. That's the start state. And then you have a final state, which is where you end up, which is where you would want to end up at, which is called, which was state B. And you can have more than one final state in such a system. And this is what it looks like. So you usually denote a start state with this triangle thingy over here. That's a start state, and then you perform a bunch of actions. So you do action one, you go to state, you go to the second state, you do another action, you go to another state, and do another action, you reach something called as a final state. So final state is usually modeled by a double circle like this one right here. So this is what an automata basically is, and we'll be using this to sort of understand like a very simple concept, but the fact that it's so simple makes it extremely powerful in a lot of other things. And anything in generally in computer science can be modeled as an automata. So like at the lowest of the low levels, you can model everything as an automata. So it's a pretty nice way to look at things and understand what is what and how things are happening under the hood. It provides a good abstraction basically. So a few some lingo in to understand further. First, there's something called as a desired state. So a desired state is something that you would tell your system that, okay, I want to be here at a certain point of time, you haven't told it yet what to do to get there, but you've just said that, okay, I want to be here. So for example, a desired state could be, I want a 3-day weekend. So that's a desired state. No, it's impossible to get to, but that's still a desired state. That's a valid example of a desired state. So there is something called as mitigating actions. That's another very, very fancy term, but what it just says is that mitigating actions are just normal actions which take the state that you currently are and it drives the system to the desired state. So mitigating action would be something like, don't do this, but like if your desired state is like a 3-day weekend, a mitigating action would be to induce a band somehow. So that's the whole idea behind it. Then a state match is if your current state matches with your desired state. That's called a state match. And if your current state does not match with the desired state, that is called a state drift. So this is just some of the lingo that's used to explain some of the things later on. So yeah. So it's just a lot of fancy terms, but fundamentally it means something simple. So desired state, as I said, where we would like to be. Mitigating actions is actions leading to that state, desired state. State matches if current state is equal to the desired state, and state drift is if current state is not equal to the desired state. And yeah, this is Kubi as usual being reaffirming. So now that we have some notion of what an automata is, we can factor in some of that terminology that we just learned into our existing model. So what I mean by that is, if you have like a start state and then you have a bunch of actions which is being performed. So the orange states here represent state drift, because if you are at that state, you are not in your state. And if your final state is your desired state over here, if you are at one of these orange circles, means that you are not at your desired state, which means there's a state drift which is there. But if you are at the green circle or the green state, that just means that you are at your final state or you are at your desired state, which means there's a state match, which is the terminology over here. So state match and state drift. Yeah, so you have a state drift here, state drift, and then finally a state match over here. So just to like reiterate, is this fine so far, or is it getting too technical?
Yeah, it's fine.
So like just like unmute and like, bro, like what are you saying? If you have questions, just do that. I did that in college once. It didn't go as well as I thought it would. I think Sachin is there. Yeah, he can tell. So state drift, state match. So okay, so yeah, and as I said, so we'll be talking about what a model essentially represents in something like this, what computation is, and what that whole term together means. So a model is something that you would use to represent a process which is happening. So like you can consider an automata to be a model basically. So that's what a model. So it's something that abstracts away a lot of the details, but it also provides you with a working understanding of how things are. So it's basic for to put it in like more known terms. If you do import TensorFlow and use some model there, don't do that. But yeah, so that's basically what a model is. It abstracts away a lot of the details because you don't need to worry about what the math is underneath. You don't need to worry about what's happening underneath. I mean, not a lot of people worry about it also, but that's what basically a model, you can think of a model as. What is computation? So computation is basically you are driving your system from one state where you have some amount of data or you have some amount of insights to a state where you can transform this data into information. So like you're processing something which is you're doing something on the data that you have available to go to a state where that data is more organized, and that more organized form of data is called information. So that's what you're basically moving from. So you're moving from a state of data to a state where you have more actionable or more usable information. And off, we know what that means. So that's what a model of computation is, and we'll see what model of computation we'll be using for today. So yeah, an automaton is just like the singular form of an automata, and each automata has a state. So what state are you currently in? So like, are you at state A? Are you at state B? Are you at some other state, or and so on? So like, that's a state. So each automata has a state attached to it. Now, you can give a command to the automata, and that automata can act on that command, and that will affect the state of your system. So yeah, that's so far that's what we've built up to. Next, another thing that can happen is you have the environment acting on the state as well. So something in the environment might change, which might lead the state of a system also to change. And these are two separate types of actions. So one is called an intended state change, which is basically your command, which is, so you are giving a command to the system saying that please change this state. So it's an intended thing that you're doing. It's not that this change is uncalled for, or it's not recognized yet. But when the change comes from the environment itself, that's a change that you haven't issued. That's a command that you haven't issued on the state. So that's something called as an unintended state change. And because of this unintended state change, the state of your automata might change. And this is something that's very important to distinguish between imperative and declarative, which we'll cover soon. But this environment state change, what you can think of is, if you have something like a self-driving car, um, so your intended state change is basically what is already developed into your car system. But an unintended state change is whatever else comes around it. So like, there might be like a pothole, or like a cow might walk through, and this is something that the system might not have prepared for, but still nevertheless it changes the state of your system. So this is what is called an unintended state change. So okay, so this is like the basic model of computation of to understand what imperative systems and declarative systems are. So like, moving on to like what they actually are. So in imperative systems, the user knows the desired state. So desired state is something that you want to get to and you want to achieve. The user knows what it is one thing. Then the user also provides commands to reach that particular state. So the user, whatever state changes happens, whether it is intended, that is by the user itself, or if it's unintended, that is something else might happen in the environment or around the current state, that to account for all of those changes and to finally drive the system to where you want to be, the user is the one who issues the commands to like make that change happen. So and another important term here is something called as a processor. So the thing which actually executes these commands that the user issues is called the processor. So like, you can think of it as like your laptop or your PC or whatever. So it has like a CPU chip, and that has a processor, and you type like a command. You develop a Python program which, like, say you say print hello world, that gets compiled, that gets interpreted, and then finally you have like a bunch of bytes or a bunch of bits which come out, and then you give that to the processor, and the processor actually executes this command. So that's what a processor is, and that the same terminology is used here as well. So what does this system actually look like? So this is what it looks like. Can I hide this? Yeah. So you have your user, which is Kubi, and then Kubi issues commands to the processor. So you issue a command to the processor acts on that command, does a state change, comes back, and whatever state change happens is sort of fed back to the user, so that the user knows that okay, now this is the state, but I know what my desired state is. So now I should know what command to issue next. That's what it looks like basically. and the user knows the desired state. That's like an important point here. And also the environment is acting on the state. So like whether it's based on commands or something else going wrong in the environment and changing the state, not necessarily going wrong, but something that you might not have foreseen or things like that. So all of those changes are fed back to the user, and the user then would see that, okay, now this is the state I am in, and this is the state I want to get to. What command would be most appropriate to get there? So when would you use such a system? Basically, when would you use an imperative system such as this one? So what you would do is, so a good chance, a good example of this would be when the number of unintended state changes is low. So like if your system is sort of isolated, where the effect of the environment um, is not as uh, significant as intended state changes, then you would use something like an imperative system, because it's easier for the user to know what command to run, because the user itself has been responsible for whatever the state is till now, because there is very little unintended state change that has happened so far. It's all intended, it's almost all intended state change that has happened so far. So when you need, and also something like this would be helpful when you need stricter control over execution of commands. So this will become sort of more clear after I like talk a little bit about declarative systems. I should have put this slide, I think, in the after that part, but okay, it's fine. I'll come back to this. Yeah, and another thing is, uh, yeah, okay, this is a typo here. This should be when your system does not need. Sorry, that's my bad. I'll edit that. So when your system does not need, so imperative systems are not good in these type of systems. I'll talk about what self-healing and all of that is like a little later. So declarative systems, this is where things get interesting. So imperative systems are like pretty straightforward. We know that we know what's happening, we know what to get to, we issue a command to get to there, and that's pretty straightforward. But declarative systems are where things get a little interesting. So uh, declarative systems is when, again, the user knows the desired state, but once what the user can do is it can tell the system that, okay, see, this is the desired state I want. Just keep this with you and use this as reference to get to this desired state. And then the user can just walk away. The user can walk away, do whatever they want, and they can basically just not worry about it. So what the system then would do is it would take this desired state from the user, it would see what the state is, and then the system gets to decide itself what set of commands to issue to get to that state, to get to that desired state which the user provided. So the user provides the desired state to a component that is called the controller. That's the component of the system that issues commands or decides which command to run to get to the desired state. And again, the thing which actually executes these commands is called the processor, same as the previous case. But what does it look like? It looks something like this. Um, Again, you have your user here. But now the user provides just the desired state to the system. It doesn't provide a command. So the user provides a desired state, and from here, the system does its work. So the loop is over here. The loop ends here. So the user doesn't need to worry anymore about what's happening in the system. It can periodically check in to see how it's going or things like that, but it doesn't need to constantly worry about what's happening. Then it provides the desired state to the controller. Controller is what decides, um, by seeing the current state of the system, it decides, and it also has the desired state. By seeing the current state of the system and by seeing what the desired state is, it decides what command it should run to maybe get to the desired state. So after it decides what command it should run, it issues the command to the processor. The processor acts on that command and executes it, and it changes the state. Again, the environment also does its thing, and there's a loop back to the controller itself, which again sees um, what the state now is, what the state should be, and then issues commands. And the user can periodically come and check in, and so on and so forth. Now, while I was trying to sort of come up with an example to like explain this, a good one that I could think of. I haven't verified this by like Googling it, but one good example I could think of was if you have something like a robot which you've built, which sort of locomotes based on vision or like sees what obstacles there are and things like that. Uh, what you could do is if suppose it notices there's an object in front of it, that is that is the current state. So it goes to the controller. It says that okay, my desired state is to get to this point, but I should get to that point without sort of dying or like falling over or things like that. So it says that okay, this obstacle will make me fall over. So this is not what I want. So what the controller could do is it could change the direction of the robot to sort of um, move away from the obstacle and like go around it or something like that. So that's like a really nice use case of like declarative systems and how where they would be useful. And yeah, so and that whole loop which comes back and sees that okay, this is the state, this is the desired state, and reconcile it and so on, that's called a control loop. And this is like, and I didn't know this because like this is, I came across this very recently. So control loop is something that's apparently very widely used in like especially in the EC branch, that whole branch. So like a lot of these control systems topics, I'm not too sure what they mean, but like, so yeah, that concept is very widely used, and that's what is used in something like building large scale systems. So I'll talk about what that means. It's just a lot of buzzwords for now. So yeah, so that's what declarative systems are. So before demo, is that fine so far? Does that work? Okay, cool.
Yep.
So I don't see. Is Goku still here by any chance? No, I think he left. Okay. If there's a chat. Kubi, yeah. So okay, I think we can. So for the demo, so like a few things that you should know for the demo is, I won't go into too much detail. It's just something that's there in the code. So I'll just like touch upon it briefly so that there's no gap or there's no confusion that happens over there. So multiprocessing is basically an inbuilt Python module. It's used for something known as process-based parallelism. So there are two types of entities that you can run. One is called a process, one is called a thread. For now, you can just think of a thread as a lightweight process, the way Linux thinks of it. But what multiprocessing does is, if you want to start another instance of processing, it will create a process. It won't create a thread. And this was mainly built so that because of the fact that Python has some issues with concurrency because it uses something known as a global interpreter lock. I'm not too sure what it is, so because of which I'm not going to go into too much detail over here. But to sort of achieve true parallelism in processing, you use multiprocessing here. So and then the multiprocessing has a class called process, which basically creates a new process. And it creates a new process by doing something called fork. So fork is a system call in Unix-based systems, which basically copies over whatever is currently running, puts it into another process, and starts running that basically. So that's all it is. And then Flask is another framework which sort of allows you to rapidly prototype web servers and create APIs and things like that. And Get is like a type of request that you send to a REST API, REST-based API. PIDs are process IDs. So in Unix or like in any operating system, whenever you create a process, that process gets a unique ID, and that is what is known as a PID. And reconciling, this is not a technical term, but in this context, when I'll be using reconciling, I basically mean to reconcile the current state that we are in. If it's not the same as the state we want to be in, then work towards that state. So you reconcile the current state to move towards the state that you want to be in. That is the desired state, as we termed it. Yeah. So for the demo, I guess I'll just like walk through the code and run it rather than coding it live. Um, so first we have like some basic module. So this is a user-defined module, and this is what it. So this basically sets up logging. So I'll be logging some things onto my terminal to get an idea of what is happening in my program. So this is what logging does, and I want it to be extra. I want it to be extremely extra because like why not? So I've added like colors and like custom logging primitives and things like that. Uh, just I don't know why I wasted a lot of time on that one part for no apparent reason. Okay, and now we have like the actual functions. So what we do is we provide like a command line argument. Okay, before that, before we start, what we're trying to do is we will run this process and we will tell it how many processes we want running of at any point of time, how many processes we want running in the system. That's what our goal is, to say that okay, go ahead and I want 3 processes running, doing something, which is something is this, do some processing. So for now it's just like a dummy while infinite loop. You can put whatever you want in there. So our goal is to make sure that our program always has these many number of processes running executing that function. So does that make sense so far? Okay, cool. So that's what our goal is. So what we'll basically be doing is we'll give like a command line argument saying how many processes we want running, and that we will pass to Kubi, which is, and that is our desired state basically. So this state is our desired state. That will pass to Kubi. So now the user knows, as I said before, the user now knows what the state of the system, what the desired state of the system should be. And again, remember that this is the demo for declarative systems, not imperative. So declarative is when the user provides the desired state of the system, and then doesn't have to bother with what's happening in the system, and it doesn't have to issue commands itself. So now you pass the state to Kubi. Kubi then passes the state to the controller, as we saw over here. Yeah, so Kubi now passes the state to the controller over here. The controller, what it does is, this is our control loop basically. So this is like a continuous loop, and it'll monitor the state of the system constantly. When I say monitor, it just says that, okay, so if my current state is less than the state that I want. So our state right now is basically how many processes that we want to make sure are running. Our get state gives us the number of processes that are currently running. And if the number of processes that are currently running is less than what we would want, it would say that it's attempting a reconcile, and it would now it would give the processor a command, which is spawn, as we saw here. Yeah, and it gives the processor a command, which is a command. It gives it to the processor, which is spawn over here. Spawn is a function which just creates a new process, as I had explained. So like, and what that process should do is just run something. So like this dummy function, which is just an infinite while loop. I made it infinite because I don't want the process to exit and die out. I want it to like keep running so that we can see what's happening inside and things like that. So yeah, and it gives that the target, and then it says that process spawned, and it starts the process basically. And yeah, but if the state of the system is equal to the current state, then it log saying it's stable, and the number of processes that are currently in the system is equal to what we would like it to be. So that's monitor, and then processor, again, it receives a command, which over here is a function. So we can just directly call the function. So Python allows you to do that because Python also treats functions as first class citizens. So first class citizens, I'm not too sure how to explain. I think like Athar can like pitch in over here and explain what they mean
I
using
guess
functional programming and all.
yeah, I mean, basically the whole point is of first class citizens is you can treat the functions as you would treat any other data. So like in some programming languages, most programming languages allow you to pass like integers, strings, or whatever. Similarly, Python allows you to pass functions around as though they were objects. That it has like the same privileges as the other data members. So I guess that's what you probably mean by first class here, right?
Yeah, I think that's what I would think it is.
Yeah.
But yeah, so that's what. See, I just know that Python allows you to do that. So, and that's pretty cool. So like the whole concept of first class and like, yeah, and functional programming is just one big alien thing to me, which, and dude, oh my god, it's so confusing. Okay, anyway, so it allows you to pass a function and you can just directly call and you can execute, the processor executes the command as we saw, and the same, and get state basically, so multiprocessing has a function called active children. So active children gives you a list of the processes that were created from the process that you're running. So like when we do Python, this is what is this called, declarative.py. So when you do Python declarative.py and give like a process number to it, number of processes to it, that's a process by itself, and whatever it creates in turn are called its child processes. So what active children would give you is it would give you a list of the child process. It would give you, and each object, each member of that list is basically an object of type process, which is basically what we create here. And I don't really care about what is inside that list. All I want is the number of processes that are running. So I would do a len on that list, which would give me the number of processes that I want. That's the get state function. And uh, yeah, so like any questions about like the code before we go ahead and like play around with it? What, like, if you don't, it's totally cool if you didn't understand some part of it. uh, that's totally okay. So like if you have questions about what something does or syntax or something like that. Oh, also I should mention, so I've done this in a bunch of places. So what this is basically, it's something called so Python is a dynamically typed language. When I say that, I mean you don't need to do what you would do in something like C. So you don't need to do int a equals or float b equals or so on. You can just do a equals 1, b equals 2.5, and it would infer the type as int and float respectively. So, but sometimes you would want control over what certain parameters should take as the type, or you would want some amount of control over what certain variable type should be. So you can hint Python to say that, okay, this is the type here. But I don't think that Python still enforces anything. This is mainly meant for like static checkers to like figure out that, okay, if you're passing something which is of type double to something which has a type int here, it would throw an error. So I don't think Python itself enforces that. This is just to sort of provide a hint, and also to make code more readable. So yeah, that's what that means over here. And this was the like the logging thing which I was telling about. So there are like certain characters in Bash which print out things in like a particular color on the terminal. So that's what all of this does. This is not my code. Like I'm not nearly smart enough to think about this like this. This is just some code I flipped from GitHub. So and like just added whatever I thought I would use for this demo. So yeah, so this is what that does, and you need to like explicitly set stuff up over here and all. This is a lot of time waste, but like I don't know why I did that, but it was fun, I guess. So anyway, so that's the walkthrough of the declarative code. So is that cool? Okay, so I'll probably like
Yeah,
run
it's
it.
Wait, you'll be running
Yeah,
multiple processes, and each of those will be in an infinite loop.
yeah,
So won't it
yeah.
be a bit too heavy
Yeah, it definitely
to
will be.
try?
So so what happens is when I tried it out, if I run it, and then what I'm going to be doing is I'll run it, and then when I set up logging, I log the
Mm,
PIDs that are created.
mm,
So what I do is I just take some random PID, I open another terminal, and I kill it from that terminal. to see how the program would respond. But if I wait a little too long, then my laptop dies. So and I'm running Chrome, so it's Daredevil scenes max over here. Okay, it's okay. We'll try and be optimistic about this. So let me just open another terminal. Okay, kill -9. Let me be ready. Python tree, declarative. Ooh, error handling. Okay. So let's say 3 because I don't want to like kill my system or whatever. So we have our terminal ready. We have this ready. Okay, let's run it. So initially there are no processes, so it'll reconcile. It'll create new processes. It's created 3 processes, so it was 1 before. Then it's 2 now. Now it's 3, and it says it's stable. Okay, so now let's take one thing. Kill that. And as you can see, yeah, so over here it reconciles again because I killed one process, and then it created a new process over here. Stop moving. I created a new process over here, and now you have 3 again. So this is what a declarative system does. So I don't need to issue commands on my own. It knows what it should do, and it does it on its own. So okay, I just ran it again because that was a little too quick. So let's say 3 again, and run. So 1 process, 2 process, 3 process, and then it's stable now. So I'll just take like, okay, I'll take like the second PID. Kill. And yeah, you can see it saw that there's 2 now, so it'll reconcile, and now it's stable again. So it's 3 again, and so on. So that's like what a declarative system would do. But when you come to an imperative system, so imperative system, I had to do some hacky things here because like I didn't know how to like fit it into the demo exactly. So what I did was okay, I'll tell that a little later. So like for the code itself, so it's the same thing. You give like the number of processes you want as a command line argument. This should be imperative, not declarative. If NSK server were here, he would tell copy paste is the worst thing. So yeah, so you give it the same thing, and then what you do is, what I had to do was, so I had to sort of figure out a way to, like I would be the user in this case, so I would have to figure out a way to give a command to the system to run as a user because this is imperative. So to do that, there were a few things, but I didn't want to make it too complicated. So you could do either like you could set up a Unix pipe and like send in commands from one and receive it from the other end. This would be so much easier if it was in Go, but I did it in Python because like it's easier to understand. So what I did was I set up like a web server using Flask. And then again, I thought that, okay, I could set up a web server using Flask. I can send in like a spawn thing, and I can run like the monitor in a separate process. But then what happens is that separate process, if it spawns, it won't detect as children of like the other process. So it doesn't work out. So basically what I ended up doing was you run a Flask server, a server, as you would call this. You do app.run and you run it on some port. I gave 8080 over here. And now the thing just runs. So what you do is you send a GET request with the endpoint in it. So that gives it to our user, which is Kubi in this case. Kubi then enters the monitoring state. Then when it's monitoring, if it notices that the number of processes is less than what we want, it would await reconciliation because it can't do anything. The processor can't do anything by itself. It awaits something for it. It awaits some command to be issued by the user itself. So it awaits reconciliation. But if it's equal, it would say that it's stable, and it would log that and all of that. Then to spawn, there's an endpoint called /spawn over here. So and this is the processor. which executes the commands. So it executes the command called spawn, and that returns a response spawned, and so on. And get state again is like it gives you the number of things. State is like a global variable which I use to like set this thing up. So by default it takes 2, but I still like throw an error saying that I expect like a command line argument. So the code is basically the same, but then there's all of this jugaad which happens in between to set things up to make it imperative. So is that cool? Like, does that make sense? Okay, cool. Okay, so I think we can run it. Okay, we have that terminal up. Python 3 imperative. Again, let's give 3. So as you can see, there's like a Flask server started. Nothing's happened yet. So what I can do is, yeah. So for those of you who don't know, 127.0.0.1 is the loopback address. So loopback is basically, so when you issue something to the web or you issue a request, what happens is that request, you are a user which issues that request, right? So what happens is that request goes into the kernel first, and then it does its stuff and gets routed out. But in loopback, what happens is it goes into the kernel first, and then the kernel sort of loops back it up to the user, um, and it's basically for you to test stuff out on your local system. So that's the IP for it. So like if you want to ping yourself to like check if you are alive for some whatever reason, you can just do that, and it'll give you responses back. So that's what's happening right now. So call you can just have localhost as well. That's also cool. Localhost 8080 init. So this starts my monitoring. So as you can see, it's awaiting reconciliation. Nothing's happened. It can't do anything on its own, and there are no PIDs available right now. So then what I'll do is I will say spawn. So one process is spawned here, and you can see one PID coming up. Okay, that works. One more process spawn. So you can see one more is spawned here, and you can see 2 PIDs coming up. And it still says awaiting reconciliation because our desired state is 3. So let's do one more. Okay, 3 processes spawned and it says stable. So now that's the imperative. Now let's like kill the process. So kill. So now it's just said awaiting reconciliation because it doesn't know what to do, because you've killed one process and now there are only 3. So now you go ahead and spawn one more and it says stable again. And now you have 3 processes available. Yeah. So does that like make the difference between imperative and declarative sort of clear? Is that fine? Or like any doubts? So like, have any of you like come across anything which might use something like a control loop? So like, as I said, one example would be robotics. I'm just loosely throwing the term around because I'm not too sure what it means. But like, have any of you come across something similar? So like something like a control loop which occurs and things like that.
I've seen it used in drones.
Drones.
Yeah, if you get a drone to a particular position, you'll use something like a PID.
Oh yeah. Oh, that makes sense. Yeah. So like I honestly didn't know something like this existed. Like so you guys might know we have like a cloud course in like the 6th sem. So they talk about Kubernetes and things like that. But like it's not very extensive or thorough, because like Kubernetes is this huge thing which no one can fully understand in like a certain number of hours. So I was sort of trying to understand what is what and why things are the way they are. And it's something really weird. There are some really weird things in Kubernetes, and this was like one of them. So like the idea I had was that, okay, you have one system and it tells you what to do, and it sees that, okay, something is not working, go ahead and make it work. But this was like a whole new ball game, which Kubernetes was playing. And luckily I found that one blog post because of which all of this came up. And yeah, so that was like the demo part. Yeah, and
So
so
this would be
yeah,
something like you're issuing Docker commands to get some kind of cluster running. That
yeah,
would be imperative.
yeah,
And
exactly.
something like
So
Docker Compose would be declarative.
yeah, so even Docker Compose, yeah, exactly, because Docker Compose has that. I wouldn't
Oh,
I wouldn't say it's declarative because
mm,
the Docker daemon again monitors and it issues commands, but the user doesn't issue commands. So yeah, you can say it's declarative in a way. That makes sense. Also, like we're talking about like Docker and Kubernetes, so I'll explain what those are in like very simple terms. Like, don't hold me accountable to like what the explanation I'm going to give, because I'm also like sort of learning and I don't want to go into a lot of detail. So what Kubernetes is you can think of it like, if you want to run something like a website, but you suppose your website just blows up in popularity, right? It becomes extremely popular. It has a lot of users which are coming onto it every single day, uh, and the website is being served by something called a web server. A web server is nothing but a processor which is running on a computer or a system somewhere. A server is also nothing but a computer, right? So it's running on a server somewhere, but the server also is limited in the amount of capacity it can run. So now if you run something like Facebook on a 4 core machine with 8 GB RAM, then I don't think Zuckerberg can also log in, because uh, that's how much resources you would need, because Facebook is first of all like a huge system by itself, and so that's what uh, would happen. So to sort of um, alleviate that drawback, what you do is you can either buy more expensive machines. So you could buy like an 8 core machine or a 16 core machine or a 32 core machine, so on and so forth. And you can run your web server on there. So obviously you would be able to handle more users on your website now. But then again, you would run out of cache, because machines like those are extremely expensive to get hold of. uh, you would run out of cache then. So what you could again do is you could buy 8 core machines, which are common these days. Not that, I mean, it's not as uncommon as like 32 core and 64 core and all that. So what you could do is you could buy these lesser costing machines, and you could buy a lot of them. Not, by a lot I mean like you could buy like 3 4 of them, and then you could say that, okay, whenever I have like a request coming in, I would want first one to go to the first machine, second one to go to the second machine, third one to go to the third machine, fourth one to go to the fourth machine, and then cycle back. So that's one way of like doing it, and this is something called load balancing. So you could do that as well. But what then again, another issue which comes up is, uh, let's say that, so I think Athar was telling the other day that one of the startups in like Indiranagar or something, their infrastructure goes on every time BBMP does work over there. So things like that might happen very often. So there might be power outages, or like you might have something going wrong which you did not take account, which you did not take into account, or you might have the system itself crashing because of whatever reason. And this happens quite often because Linux has this very weird thing called out of memory killer. So what it does is, every time, if you're running a Linux machine, every time your memory sort of reaches its limit, it randomly takes processes and kills them and throws them into swap space. It throws them into disk. So it randomly takes and starts killing processes. So this was something that was very common a while back, and like it was a huge problem. So what then people started doing was, if you have your website, what they do is you don't have just one thing running, you have multiple instances of them running on multiple machines. So it's not just one instance of your website running on each server. You can have 2-3 instances running on each server again. So that's something called replication, and that's meant for fault tolerance. So like the term means that if something goes wrong weirdly or arbitrarily, you are still able to function well. That's what people started doing. And then again, there is another whole scenario and paradigm of something called microservices, but that's like another talk for another day. So that's what people started doing basically. And when you start doing replication, that is, you start having multiple instances of things, you will constantly have to monitor them, because you want to make sure that you have 2 instances of your website running on server B. You want 2 instances of your website running on server C, and so on. So you need to constantly monitor them. You need to constantly update them if they die, or you need to do all of these other logistics constantly to make sure that your system is up and running the way you want it to make it. So to sort of bring all of this in, Google, like a few people at Google and a few people from elsewhere, came up with this whole idea of something called Kubernetes. So Kubernetes means something called a helmsman, which is like someone who like pirates a ship, or like steers a ship or something like that. So the whole point of Kubernetes is that it will make sure that you have certain resources that you want, and they're available for your system. So if you say that I want 3 instances of my website, it will make sure you have 3 instances. If you say that I want this much storage for this particular part, it will make sure that that storage is available for you, and so on. So how does Kubernetes fit into this whole idea of declarative versus imperative? The way it fits in is Kubernetes decided to go with a declarative approach to doing all of these things that I just mentioned. So, and Kubernetes really made it really, really simple to do these tasks, because it, so as like a interlude, whenever you read about distributed systems, which are basically something that you're trying to operate, but not just on one machine, but like on multiple machines altogether. So if you have like something running on 2-3 systems or 4-5 systems, or like in real world scenarios, it can be thousands of servers altogether. The main goal that people will try and tell for distributed systems is that you should try to achieve is that it should feel like one single system to the user. That's what you should try and hope for. But in most cases, people don't care about this because it just makes their life easier. So that's like the ideal goal that you would hope for. But what Kubernetes also mostly has done is it feels like an operating system for like a large number of machines. So like it takes care of scheduling, which is like deciding where to run something. It takes care of allocating your resources, so like it gives you a machine to run things, and like it takes care of making sure things are running correctly, and it reports back if things are going wrong, so that if something it can't handle on its own, the user can handle, and so on and so forth. So when I say Kubernetes went with a declarative approach, what I mean is all you need to do is you need to give Kubernetes something called as a configuration file, which usually is a YAML file. And all you can do is you can say that, okay, this is my service. I want replicas to be 3. So by replicas, I mean I want 3 instances of this particular process running at all times, which we just saw in like the demo. So like the demo was like a very, very hacky way of showing that concept. So like it says that I want 3 things of this running at all times, and you just give it to Kubernetes and you don't bother about it afterwards. And what Kubernetes also does later on is that it has something called as control loops, which I just said, and Kubernetes calls it controllers, which also I mentioned. And what controllers do is that it will constantly monitor your state of the system. And then from that state, if it sees that something is not matching the current state, it will issue commands to make it match the current state. And this sort of makes things extremely easy in that whole complex scenario which exists when you have a lot of systems to deal with, because you don't have to constantly keep monitoring these systems, and you don't have to constantly keep saying that okay, run this, run that, run this, run that, run. You don't have to micromanage over there. What Kubernetes does this, it just says that, okay, you know what, I trust you guys, you do your thing. This is what the desired state is, this is what you need to do, and eventually that will happen. So that's what Kubernetes does, and that's a declarative system, as we saw. So controller is something called control loops. The state in Kubernetes is stored in a distributed database, more like a key value store called etcd. Uh, so etcd basically stores all information about the state of your current system. So like it'll store if you have if the Kubernetes scheduler says that, okay, I have to schedule one particular instance of the process which we just saw. So like if a process needs to come up, it will say that the process is ready and to be scheduled onto, say, server A. Now server A has like a controller which is running, which says that, oh, I see there's a process which is meant for me, so let me go ahead and start the process on my server. So that the server then goes ahead and starts the process over there, and it sort of goes on and on over there in like a very seamless and nice manner. So it's like very clean, and you don't have to worry about go continuously monitoring and seeing what is what and things like that. And the processor is something known as the Kubernetes API. So the Kubernetes API is the central point to the entire cluster. So it's the entry point to all of the components that I just mentioned, so like etcd, which is the state, the control loops, which is another component, the scheduler, which is another component. Everything happens through the API. Nothing can talk to any of these components without going through the API. The API is the entry point to the entire Kubernetes. So the Kubernetes term for this is the control plane. So the API is the entry point to the entire control plane in Kubernetes. So that's what, yeah, so the references are like this blog post which I mentioned. You can check it out here if you want. And the documentation for controllers for Kubernetes, which is this, yeah, and the slides. And so I'll make this repo public right after this talk. You can go ahead and like play around with the source code, or like if you want the slides for whatever reason, you can check that out. And so like, did the connection between declarative systems and Kubernetes make sense? Somewhat.
Yeah,
Yep.
it did, especially the program that you showed us with the system coming back online, the processes.
Yeah. So, okay, questions? Any questions? Like if anyone joined late, if you want to see the demo again or something, we can do it again, I guess. It's pretty short, the demo. So,
I don't have any questions, but I'm not sure if you guys had this, but in Sem 3 we had a language called Prolog in Automata, which they explicitly called as a declarative programming language. Yeah. And you can basically set up states and relations and facts and stuff without any of the programming parts. I don't know how relevant it is here, but
Yeah, that's actually pretty cool. Like, I've heard of Prolog, so I did not know they have changed their syllabus to include that. That's actually quite cool. The only thing I know about Prolog is it's like it's often used in like when you want to like computationally like create theorems and prove them, or like prove a certain
yeah,
state or something like that, right?
yeah.
So I think that declarative is actually quite related to this. I couldn't help but think of it also when like Madhav brought it up. So I guess the whole fundamental thing behind declarative versus imperative is that in declarative, the interface is more like the user tells what they want, while in imperative, it's more like you're telling what to do, not what they want.
Yeah.
Do this, do that. But you're not expressing the actual intention. So like pretty much almost always, if you want a better interface, in my opinion, or from what I've seen, making it more declarative makes it more helpful. So,
Yeah.
and it's weird that you said functional programming, for example, is like full on alien, but that's like one of the main principles also behind why it's done that way. So the whole point is with functional languages, you're trying to make the program more declarative than like imperative. Like the whole point is you express what you want to the program and you let the abstractions handle it for you.
Yeah. So
So
like, and
yeah,
one more thing I've seen is that if you look at something like, I don't know, Haskell, for example. So I've seen stuff like if you have a list of numbers, and if you want to get like the odd numbers from there, you can do something like X arrow X mod 2 or something like that.
yeah,
So like you're not saying use if over there, use the if construct, use it in this way. You're just saying that I want X, but X should be such that X mod 2 returns something that evaluates to true in that particular programming language. So
exactly. So like
yeah,
you pretty much like got it nail on the head. The whole thing is like in an imperative way, the way you would do it is you would not think about what you want. You would want like odd numbers in a list, right? But if you're doing it in C, how you're going to tell the C program is not get me odd numbers in the list. The way you actually express the intention is for every single index in the array while you're going through one by one, check if the index like the value held in that index of that array mod 2 is equal to 0. If it's
yeah,
true, then out print it out. So like
yeah,
you're telling what to do, but maybe in like a more functional programming language like Haskell, you would probably do use something like a filter, right? Like so you just
mm,
say um, pass this list through a filter such that the filter captures this certain condition. So like your condition is it being even or
yeah,
odd or whatever, right?
mm,
So I think like that's kind of like raising the level of abstraction. It makes it
yeah.
easier and it's like less error prone.
It so and this sort of makes me realize one more thing. So like, if you raise the level of abstraction, you have lesser control
Yeah,
over what's going on. So if you want to code for say performance, or if you want to optimize the way your code runs, so like for example, what you can do is if you want to count the number of odd numbers in your list, right? What you can do, if you just write the Haskell way, then you don't really know what's going on underneath. But if you would want to optimize certain things for whatever reason, so like assume that's like a super important program, like performance critical, and like it has to run in this much time, and so on. So writing in an imperative way is better there, because what you can do is branches. So like if when I say like the if statement and all of that, they are converted to what are known as branches in assembly. And then branches usually tend to be expensive, because you can either have uh, like this whole concept of pipelining is there, and then you need to flush the pipeline if you have a misprediction, and so on. So like basically all you need to know is branches tend to be expensive. So instead of having like an if a of I mod 2 equals 1, count plus plus, what plus plus count, because that's more optimized. What you can do is you can just do count plus equals a and 1. So if it's an odd number, a and 1 will return 1. So you can just increment the count there. Or if it's an even number, it'll return 0. So it won't really matter to the count. So like for things like that, if you want that fine grained control in that case, imperative is sort of the way to go, because it gives you more control. And that's sort of true for any form of system or program that you're writing. So like more abstraction means lesser control. So
I think I would like to like add a caveat or like contest that a little bit.
hmm,
So it is true that if for like your specific case you're trying to do that, but there's like one way to deal with this because you're losing control. First, you have to make sure your implementation underneath that abstraction is good. So it's possible to make like the right optimizations to make things fast. And usually the thing is you like kind of pay that cost of performance a little bit upfront to like make things scale better and make things more maintainable. So let's just take like the Kubernetes thing for example, right? It is possible that if someone like issued commands in a certain way, they might actually outperform like whatever the control plane of
Yeah.
Kubernetes is, right?
Hmm.
So, but then the problem is if once you like, it'll work fine. Like you'll be faster and you'll beat the Kubernetes like automated system for like maybe 5 or 6 pods or whatever that are being deployed. But if you're going to scale that to like 1,000 or 10,000, right? It becomes like extremely chaotic and like manually doing it becomes like really hard. At beyond a point, you can't scale at all. So
Yeah.
the thing is, compared to like the performance you're going to get by distributing an operation over like 10,000 things, right?
Hmm.
You're enabling that in the first place by making it declarative, because then you're able to maintain that, and like you're just paying
Yeah.
that, like the price of handling that small thing is very negligible to the performance gain that you get like deploying a lot of things.
Yeah. So there's always that trade-off involved. So like, uh, it's always better to like let go of certain performance benefits when you have to scale up. When you have to scale out, rather. Scale out is basically buying more servers, as I mentioned.
Yeah.
So than if you're like on a single system. So yeah, I forgot what I was gonna say, but yeah, that's pretty much it. So like, if you have something like so for example, if you remember in C, you can reorder fields of structs in certain ways to like optimize memory usage, but people wouldn't do that in Kubernetes, in something like Kubernetes or projects that are that big, because what people usually do is they group fields and structs together that are related, so that it's more documentable and it's more maintainable and readable that way. So like, having that small performance gain over there is not of that much significance when it comes to like
Yeah, it's like a
huge
premature
systems.
optimization,
Yeah,
right?
and like
Because
the
you're
if you read,
preventing further possibilities of scaling by
yeah,
like, yeah,
and like if you read any like I forgot, I think John Bentley is the guy. So like he's the guy who like talks a lot about optimization and all. So like if you read his website, he's like there are three rules to optimization. First one is don't do it. Uh, Straight up don't do it. Second one is uh, think about it, think about it again. Uh, Lean towards not doing it. Third one is okay, fine, do it if you have to. So like optimization is like something uh, there are other costs which come with it. So like if you spawn more threads to like parallelize, you have less CPU for other things to work on, and then there's like this whole other jungle which you have to deal with in terms of
yeah,
optimization. So like, yeah. So but yeah, this whole concept of declarative things just makes stuff a lot easier. I don't think Kubernetes would have worked out if it was imperative, because it's not possible to like the interface it provides is extremely easy, and like the uh, Kubernetes is extremely extensible. So when I mentioned something called a control plane in Kubernetes, what that basically is that all of those components in Kubernetes. So like you have the API server, you have the scheduler, you have etcd, all of that. So what you can do is you can just take the Kubernetes scheduler and yeet it, just chuck it out, and plug in your own scheduler over there. And that's possible because Kubernetes has like a very strong principle of saying that we will not support hidden internal APIs at all. So whatever the user interacts with Kubernetes, the same APIs Kubernetes uses to interact with itself. So declarative systems sort of made that very easy to implement for Kubernetes, because you don't have to micromanage all of these things that are available. You can just sort of trust these components to do its thing and work together. So yeah, it's pretty cool. Uh, Wait, is there a feedback form for this meetup that we can put up, or we can just put it on Slack? That's cool.
yeah. I don't think we have made it yet, so we'll just put it on Slack right after this.
Cool, fine. Okay, cool. I think we can end it. Or like, is there anything else that we can like, if you want to chill or like talk about something or anything of that form? I think no, I think you can stop the recording and then we can carry on
Yeah.
with whatever.